is Nima Farzadnia from Missouri University of Science and Technology. And the title of his talk is Mechanical and Microstructural Properties of Cement Pastes and Rice Husk Ash Coated with Carbon Nanofibers using a natural polymer binder.
Yeah, my name is Nima Farzadnia. I'm a researcher with Missouri University of Science and Technology. And to be very honest with you, during my PhD, which was about nanomaterials, like around 2009, 2010, I had a lot of problems with agglomeration of nanomaterials. That was the idea came to me to develop something very easy to disperse nanofibers, nanomaterials, with the help of my very good friends, Dr. Asadi, that is environmental science engineer, and Dr. Rosini, which is who is a chemicals engineer, actually. So the thing is that all of us here know that carbon nanofibers are the materials of future, strategic material, functional material with high tensile strength, high aspect ratio, high specific surface area that can be used to inhibit the crack propagation, act like kind of like bridge for cracks, and also with ultra electronic behavior, high thermal conductivity that can be used in self-sensing applications and damage detection. These materials they have customizable surface that we can increase and kind of like modify the interaction with cement matrix. However, there is a big problem with CNF. The fact is that, as you can see in this figure, if we use excessive amount of nanofibers, for example, here, like up to 0.5% nanofiber, you can see that there is a decline in mechanical properties. Like it is reported here by Wang in 2020, we have a huge decline of compressive strength, of flexural strength, and splitting tensile strength. So first, we have to come up with a kind of like remedy for that. So far, we have introduced different types of dispersion techniques. For example, physical dispersion methods like high-speed shearing or ultrasonic dispersion, which has been with us since 2008, I guess, and chemical dispersion method, which is a little bit more advanced, like surface covalent bond modification with a strong acid treatment, or non-covalent bond modification with surfactants. So, or combination of this physical and chemical dispersion methods that everybody here, I'm sure, that are very familiar with. There is a third approach, which is in situ growing of carbon nanotubes or carbon nanofibers on cement or supplementary cementitious material particles that are actually, we call them silica substrates. These are some of the works that have been, some efforts that have been made actually, for example, to cover carbon nanofibers on cement particles, or here on fly ash, or here on silica fume. Mostly there are two very known methods, which is called chemical vapor deposition method and microwave irradiating conductive polymer method. In both systems, we are using some carbon sources. For example, in the former method, we use gaseous hydrocarbon, while in the other one, we use cyclopentadienyl as, like I said, carbon sources. In both methods, we use a high temperature with presence of silica substrate and a catalyst. For example, for this method, this temperature is provided by microwaves, which is much faster than the former method, but at the same time, it is energy intensive. Both methods actually are. So these methods are really functional, even better than physical or chemical dispersion techniques, because we are covering our particles with carbon nanotubes or carbon nanofibers. But like I said, they need high temperature, which is energy intensive, and at the same time, they can be expensive because the process is kind of very lengthy. So the idea of this presentation actually is introducing a novel dispersion technique using Chitosan. Chitosan is a very cheap let's say, polymer, which is second most abundant biopolymer next to sugar, and it is biocompatible, biodegradable, and it is very well known for its cross-linking properties. This is actually the property to link carbon nanofibers to the surface of rice husk ash. So we produce the rice husk ash ourselves with at the temperature of 650 degrees Celsius with a heating rate of 200 degrees Celsius per hour, and then we pulverize the rice husk ash. The CNF that we use was commercially available CNF, and you see the microstructure here that is provided by the manufacturer, that was Outrage Sigma, with a surface area, specific surface area between 35 to 45 square meter per gram, and the length of 50 to 100 micrometer and 50 to 150 nanometer in diameter. Well, the significant part of this study, in my opinion, is the very simple processing of coating rice husk ash. As you can see here, the process can be very easy, very simple, and can be done in all labs. What we did actually, first we removed the impurities and some metallic ions from the rice husk ash, and also we oxidized the CNF surface using nitric and sulfuric acid, like for 48 hours. After that, another problem was improving the dispersion of carbon nanofibers, and we used acetone solution for 24 hours. So we stirred and submerged carbon nanofibers in acetone so that it kind of like improved the dispersibility of this carbon nanofibers in next steps. And then we mixed this carbon nanofibers and rice husk ash in a solution of, solution of Chitosan binder, and stirred that for like 1 hour, and then over dried and modified that at 70 degrees Celsius. The weight ratio of carbon nanofiber to rice husk ash was like 10%. So the first important thing for us at this moment was the fact that, okay, is the process done completely? Is rice husk ash or particles are covered fully or not? So we did series of microstructural analysis. For example, the SEM test here, these are the naked rice husk ash as you see here. And this is very clear that the surface is like uncoated. And these are the samples that we did SEMs on, and it shows that how the carbon nanofibers are coated the surface, and you can see that the distribution of this coating was very evenly on the surface. The fact is that when we saw this, the idea came that to our mind that, okay, so when we had the idea of this rice husk ash, the purpose was to use rice husk ash as a carrier, as a vehicle for carbon nanofiber, and at the same time, we could use the supplementary cementitious material characteristics of rice husk ash in terms of consumption of calcium hydroxide, or let's say render of a stronger calcium silicate hydrate. So we did other tests to make sure that rice husk ash still has its own intrinsic properties. We did the pore size distribution, and we realized that, well, as you can see here, this is before coating and this is after coating. And we realized that, well, the porosity, the pore structure was filled with this coating, and it was not, the rice husk ash was not as porous as before. It gave us the idea that, okay, so it is going to affect the reactivity of rice husk ash. With this series of tests, I don't have all the results here. This is only the proof of concept, honestly. So we did a TGA test with presence of modified rice husk ash and calcium hydroxide powder to check the consumption of rice husk ash, and other tests actually. But a more clear test here is this calorimetry analysis and heat evolution analysis. And as you can see, when we added 15% coated rice husk ash comparing to the same amount uncoated or unmodified, the heat evolution reduced, and as you can see, that we have the reduced reactivity of rice husk ash after coating. So the next step was see the effect of this coating process on fresh properties. So we did the flow table test according to ASTM C230, and we realized that unlike uncoated rice husk ash that decrease the flow values, which is actually a demerit of rice husk ash, our coated rice husk ash actually increased the flow values. This could make using rice husk ash actually kind of easier and more workable when we are dealing with concrete pouring and other stuff. And about the mechanical properties, that actually was the initial purpose. We tested compressive strength, and we realized we actually experienced very interesting results. As you can see, inclusion of coated rice husk ash increased the compressive strength by 60%, especially at later ages that the bond strength was developed fully. And the other thing that we can refer to here is that for both uncoated rice husk ash and coated rice husk ash, the amount of 15% was kind of like a threshold. However, when we added carbon nanofibers on the surface of rice husk ash, we could increase that threshold up to 20%. This is also another advantage of coating carbon nanofibers, that we can use rice husk ash in higher dosages actually. But more importantly is the performance of this coated rice husk ash on flexural strength of paste. And so we did the flexural test according to ASTM C348. And again, the results were very interesting. As you can see, when we have 5% coated rice husk ash, we have almost like 45% increase in flexural strength comparing to the counterpart of uncoated rice husk ash, which is kind of like promising results. All this results from flexural strength and compressive strength is a kind of like showing the fact that carbon nanofibers had a better dispersion as a coating on rice husk ash. The other derivatives of flexural properties was toughness and modulus of rupture. Toughness as the area under the curves from flexural strength, and you can see that this modified 5% of modified rice husk ash increased toughness by 170%, even as early as 3 days. And this amount was almost like 60% increase in modulus of rupture at 28 days. And I want to bring to your attention that these comparisons are with uncoated rice husk ash. And if we look at the controls without rice husk ash and without carbon nanofibers, we can see that extent of improvement is even more than that. The other important properties of flexural strength, the derivatives from flexural strength, was ductility. It means that the area under the curve after the first cracking. And you also see that the increase in ductility from rice husk ash coated with carbon nanofibers was up to like 100% at the very early age of 3 days, actually, if you compare it with uncoated rice husk ash and control with no rice husk ash and no carbon nanofibers. But like I said, we knew that because of coating process, the reactivity of rice husk ash was decreased, and it was mostly the physical effect of carbon nanofibers in bridging the cracks, for example, or inhibiting the crack propagation under loading. So we also wanted to look at the phase changes. We did different tests, XRD, TGA, FTIR. Like I said, this is a proof of concept. I'm only showing you the FTIR results, and we use curve fitting, actually, peak fitting. And this presents the convolution of the results at from 800 to 1200, which is related to SiO calcium silicate hydrate. So for me, the important cues is Q2, which represent the SiO stretching vibration, reflecting the high density calcium silicate hydrate. By high density, I mean the calcium to silica ratio is around 2, and Q3 and Q4 that are dealing with incomplete hydrated calcium silicate hydrate, that they have higher SiO2 content. Very quickly, if you compare control with no rice husk ash, with no carbon nanofiber, and the one with uncoated rice husk ash, and the one with coated rice husk ash with carbon nanofiber, we realize that when we are adding carbon nanofiber coated rice husk ash, we have a decrease in Q3, the area percentage, from 46 to 39. It means that lower reactivity of rice husk ash actually kind of like reduced the formation of high density calcium silicate hydrate. The results were also confirmed with the other tests like NMR. But at the same time, still the effect, as you see on Q2, is more significant than the control samples with no rice husk ash and no carbon nanofiber. The same thing can be seen for control and other samples at 28 days. And this time, I want to bring to your attention about the changes in Q3, which is about incomplete hydration of calcium silicate hydrate. This time, this incomplete hydration is kind of like lower than the ones at the first day. It means that progressive hydration and increase the duration kind of can compensate the lower reactivity of rice husk ash coated with carbon nanofibers.
Nima,
very quickly.
Thank you.
This study confirmed the effectiveness of proposed dispersion method, but mostly through physical effects. The SEM images show the uniform distribution of carbon nanofibers, and results from mechanical properties like improving ductility, modulus of rupture, toughness, show that the failure mode shifted from strain softening or quasi-brittleness to pseudo strain hardening. Thank you very much. I'm sorry that I just put a rush in my presentation, and this work is an interdisciplinary study that is conducted from 3 fields of civil, chemical engineering, and environmental engineering. The results are published, honestly, but I thought that now that carbon nanofibers are getting more attention, especially for 3D printing, knowing about available techniques that are easy and cheap could bring some values to this research. This is the barcode of my Google Scholar. I have related studies in this, and I would be happy to be sharing that. Thank you.